Okay, so we're going to figure out the energy balance for a spherical object um, receiving sunlight. It turns out that you can actually rewrite the equation for the relationship between temperature and the energy released by a spherical object into a relatively simple form. And so if I have, let's say I have, I'm looking at the ground of the Earth. So, and then let's imagine that it has some temperature. The relationship between the energy out of that object and temperature, I said went as temperature to the fourth. More specifically, the extra constant we have is 88.5 Kelvin. So that's Kelvin, and this is raised to the fourth power. Okay, so given the temperature, I can find the energy out. Given the energy out, I can find the temperature. I can just simply solve this, and what I'd get is energy out. I can raise both sides to the 1/4 power or to the 0.25 power times 88.5 Kelvin. That would be equal to the temperature. Okay, so those are the relationships that we're going to actually use. So this is true if we assume, say for the Earth, that we have 100 units of solar energy coming in. Now, also for the Earth, you know, the Earth reflects about 30% of the energy, so 30 just bounces right off, goes back off into space. Now I'm going to assume for right now that there's no atmosphere. We'll do another example with an atmosphere shortly, and then you'll see the effect, the greenhouse effect. The rest, so 100 minus 30, the 70, gets absorbed in the ground in the Earth, and that raises the temperature of the Earth. As the temperature rises, the Earth radiates in the infrared. And what will happen is the temperature will keep going up until there's an energy balance. So there's some energy out that will happen when things are in balance. In order to determine the energy out, we simply say we look at all the energy in, make it equal to energy out. That's what will happen in the balance. Here we have 100 minus 30, and the only energy out we get is this E out for the surface, and so this is equal to 70. 70 is equal to E out. That's the total. And then I can determine 70 to the 0.25 times 88.5 Kelvin. That's equal to the temperature, which is equal to 256 Kelvin. Okay, so that's the temperature that the surface of the Earth would get to without an atmosphere, with 100 units of solar energy coming in, 30 bouncing off, yielding 70 coming in total, and then the Earth heats up until the energy out is equal to 70. If, for instance, it heated up a little bit more, what would happen is the energy out would then be greater than the energy in, and that would cause the temperature to go back down to 70. If the temperature were to drop below 70, the energy in would be greater than the energy out, and the ground would heat back up to 70. So this balance is achieved at 256 Kelvin. So if the temperature goes above 256 Kelvin, it'll cool back down. If it goes below, it'll warm back up and maintain this balance on average. Now this is true without an atmosphere. The next tutorial looks at the case when we add an atmosphere, and we'll see how that changes things.